not students and who are somewhat more experts in the subject will still be able to take away some little bit from this talk. But this talk is very non-technical and aimed at a much broader audience. So I should begin with saying that. When Sudhanshu asked me for a title, I chose this title, and it's where do we come from, what are we, where are we going? This is the same thing in French up there. This is the title of a very, very famous work of art by a French artist called Paul Gauguin. Paul Gauguin was an impressionist painter from something like the end of the 19th, early 20th century. And he spent a good part of his time working in Tahiti. And when he was there, he made this very famous painting. And the title of this painting is exactly the title of my talk. Where do we come from? What are we? And where are we going? I chose this title because these are questions which are very, very fundamental. So fundamental that these have pervaded through times, and it has been the concerns of many, many civilizations across millennia. And when we look at it today, this is, I feel, another representation of those same questions. And if you're right at the, sorry, if I move away, then I will lose you. But right at the, there it is. Right at the origin here is the Big Bang, and that is basically the question of where do we come from, and these elementary particles that populated the early universe. So these particles that populated the early universe answer the question of what are we, and the evolution of the universe itself is about where we are going. So, I mean, the choice of the title that Gauguin made for his painting, it shows how profound it was, because it's a these are questions that are not of any one epoch, or not of any one history, or not of any one culture. These persist through ages. And these continue to be questions. I mean, we seem to have some answers, but they continue to be still very interesting questions. So I'm going to start by talking about atomism. Atomism is actually, contrary to what some of you may think, it's a very, very ancient idea. It's an idea that goes back 2,500 years. And it's an idea that first took birth in philosophy. The Greek philosophers, Leucippus and Democritus, were the people in Greece who at that time thought of this idea of atomism. And it has also a lot of resonance here in the India of that time, 2,500 years ago. There were Indian thinkers who worried about the fact whether all matter is made of atoms. And it has continued to exist across cultures. In Baghdad, for example, the Asharite traditions in Islam have also talked about atomism. And atomism is the idea that all matter is made up of some small indestructible units. And it's an idea that tries to resolve this paradox of the conflict between the ideas of being and becoming. Being and becoming meaning, on the one hand, we feel everything is quite the same. The world is exactly the way it is, nothing has changed. And there is a whole philosophy of being that comes out of that. The other philosophy which asserts the idea of becoming, which says that nothing remains the same, everything is constantly in flux, everything is changing all the time, and you cannot step into the same river twice and so on. And what is the resolution between the two? And the atomists try to put a resolution between these two, because what they claimed was the phenomenal world, the world that we see every day, is the world that is continuously changing. But beneath this phenomenal world, there is another world, and that is the world of the atoms. And that world is eternal, and nothing changes. So in some sense, it's a way of resolving this big conflict between two ideas. And skip this a bit because we all know about Newton, and the point about this slide was essentially to say that atomism had to wait a long time before it had to come into science, and science itself, modern science as we understand it now, took place with people like Galileo, Descartes, and Newton. And Newton in particular gave us the laws of motion on the one hand and the understanding of gravity on the other. And that was actually that could actually mark the birth of modern science as we understand it. But we also know that there was this other great revolution in physics, and this great revolution was due to the Scottish physicist James Clerk Maxwell. And because in Maxwell's time in the 19th century, people had started discovering beyond what Newton had already understood about gravity. People had discovered new phenomena related to electricity. On the other hand, there was also magnetism, which was known for a very long time. And for the very first time in the early 19th century, people started realizing that maybe these two things, electricity on the one hand and magnetism on the other, are not so different after all. They started seeing similarities between these two, what are apparently very different phenomena. And it was Maxwell who eventually gave us a unified theory of electricity and magnetism. So basically the idea that if you have a electric field which is varying in time, which is changing in time, then that electric field can generate a magnetic field. And the fact that a changing magnetic field can generate an electric field. These were things that had been observed, but Maxwell tried to combine these two and ask the more important question of what happens when you have both magnetic and electric fields varying at the same time. And then he discovered that once you have that, what can happen is the variation of the electric field can sustain the magnetic field, the variation of the magnetic field can sustain the electric field, so much so that they can become independent of any material. Because normally you need a wire to conduct electricity, you need a magnet to hold magnetism. But here the time variation of these two things can sustain each other. They can become independent of the material and propagate as electromagnetic waves. What we normally understand as light, and this is a very quick summary of the electromagnetic spectrum with some length scales put in there just to give you an idea if you have not seen this before. And we are going from the left to the right, from the long wavelength or the long wavelength side, small frequencies, to the other side which is small wavelength and large frequencies. And as we know, this side, left side of the spectrum is called the infrared, the other side is the ultraviolet, and in between where you see the colors is the visible spectrum, which is the usual Ravenshaw spectrum that we are all familiar with. So as I was saying, atomism has had a long history, and even the idea of elements had come down from the ancient world. But especially with the discovery of modern chemistry, the ideas of atoms made a comeback into science, and especially when it went a long way in helping us understand the systematics of the periodic table. And we are all familiar with this school book depiction of an atom. I've chosen to show the figure of a carbon atom, for example, with protons and neutrons held in a central nucleus and electrons orbiting around it. So the properties of the element, the properties of the chemical properties are essentially determined by the electrons that are orbiting in the nucleus, around the nucleus. So in fact this is a very, very bad drawing because it's completely not to scale. The nucleus is very tiny, it's a factor of something like 100,000 smaller than the first orbit of the electron. So this is a very gross depiction of an atom. So the understanding of, sorry, let me go back here. The thing is, when the transition was made into trying to understand the atom, that was the first time that people realized that after some 250 years of Newton's mechanics, that maybe we need to have a new kind of mechanics put in place. Okay. So I'll do a short detour here to talk about particles and waves. And this is something that is talked about very often in the context of quantum mechanics. The way I like to think about it is to say that particles and waves are two kinds of models that physicists like to work with, or rather these are almost the only two models that we can really work with. And what are particles? Particles are those objects which give you a definite answer to the question, where is it? If you ask me where is the chair and I can point out and tell you this is where the chair is, then in a certain sense, this chair is a particle. I mean, at the distance that I am from it, the dimensions of the chair are irrelevant and I can point out and say that is the chair. A wave, on the other hand, is something that is spread over a whole dimension. So if I have a wave sitting on a string, then it's not some point on the string that is a wave, but the entire disturbance across the string which is a wave. So these very localized entities which are particles and these very extended entities which are waves have been the two kinds of models that people use in physics to describe things. So Newton's mechanics talk about particles, and in a sense use particle ideas to even describe very, very big objects like the planets, when the orbits around the moon and so on, but in the orbits around the sun and so on. But on the other hand, when Maxwell had to describe electromagnetic phenomena, electromagnetic waves, then he used the idea of waves, which are these extended objects not localized at one point of space. Okay? The question was, when you go down to something as small as the atom, you have to first learn to visualize how small the atom actually is. If you take, in fact, one centimeter division on your scale and divide that 100 million times, then each small division is the size of an atom. Okay. So the question is, when you go down to those kind of sizes, does our understanding of mechanics work still in the same way as Newton had first formulated it? And it was a surprise when it happened, but in hindsight it's not much of a surprise that it didn't work. It is because we were pushing ideas from the microscopic world to this very, microscopic domain and trying to see whether what we understood in the macroscopic world works. In particular, we wanted to ask, we thought that the electrons are describing matter. I mean, if I take chunks of matter, they are made of atoms, and eventually those atoms are made of electrons. So electrons should share some of the same things, same properties that we understand matter to have, which means that if we describe matter in terms of particles, we should be able to describe electrons in terms of particles. That understanding turns out to be false, because the electron itself is some kind of, I would like to use the word transcendent entity. It is neither a particle nor a wave. It's something described by some mathematical function, and it's our limitation that we try to understand, to grapple with it in terms of a wave picture or a particle picture. Okay, and so this calls, in short, this microscopic world calls for a new understanding of motion, a new understanding of mechanics, and that is where quantum mechanics comes in. And you must have heard of the uncertainty principle and so on, but I will not get into that right now. If you have questions about it, you can ask me. The other major revision of Newton's mechanics came from quite a different direction. And this was with Einstein's work in relativity. And it was realized that whatever we had understood of motion, or whatever Newton had understood and formalized about motion, had come out of looking at objects which were moving rather slowly, at objects which were moving at speeds which we normally encounter. But when you go to things which move at very, very high speeds, like light moves at an incredibly fast speed, it moves at the speed of something like 3 lakh kilometers a second. And at those kind of speeds, again, Newton's mechanics don't work quite the same way. And that calls for a revision of Newton's mechanics, which leads to what we call special relativity. And in particular, if you want to also make gravity compatible with this whole picture of special relativity, then you have to go into something called general relativity. This is all the background. I'm rushing through this, I'm aware of, but okay. But somewhere in the 1930s, when quantum mechanics was formulated, and we understood that the microscopic domain has to be described by this new quantum mechanics, we thought the game was over. Okay, that we understood everything, that all of chemistry has been reduced to physics, and physics has provided a very neat answer for the understanding of matter and energy. So at that point, there was a moment of completion. There was a feeling that this was the end of the game, sort of. In spite of the fact that there were obviously new things waiting to be discovered. Okay. But the picture of the world was very simple. Everything that we knew in the world was made up of atoms, and these atoms just had 3 kinds of particles: a proton, positively charged; the electrons, negatively charged; and the neutral neutrons. The neutrons and the protons sat inside the nucleus, the electrons orbited around it. So this was as simple as the world can get. Just 3 particles to understand the whole world. But even when we look at this very schoolbook depiction of an atom, we realize that this cannot be the whole story. And that is because you see that, as I told you, that this is all trapped in a very, very tiny amount of space, in some distance scale which is of the order of 10 raised to minus 15 meters. So how is it possible for a clump of a bunch of positively charged particles called protons and neutral particles called neutrons, what is it that makes them hold together in such a small space? Protons are all positively charged, so they should repel each other and fly away. Why are they sticking together then? And the answer to that was obviously what gave birth to this whole subject of nuclear physics. And this Japanese physicist Yukawa, who said that protons and neutrons actually are held together inside the nucleus because of some very, very strong nuclear interaction. And because it was a strong nuclear interaction, it got called strong interactions. And these strong interactions are mediated by new kind of particles called pions. And this was what Yukawa had predicted, and he predicted these pions would actually be seen in experiments. And lo and behold, they were actually seen in kind of experiments I'll just talk about in a moment, called cosmic ray experiments. And already by the 1940s, a new particle had been discovered beyond the usual electron, proton, and neutron. So the world was already beginning to get a bit complicated. Then there was something you must have also encountered again in school, which is called beta decay. You might even have heard of the word big interactions. And this is where interactions of the kind where nuclei of one kind, in this case, the cobalt nucleus, which has 60 neutrons, becomes a nickel nucleus also of 60 neutrons, but with different numbers of protons and neutrons. Okay. So why do these kind of interactions happen? People started seeing these strange interactions where negatively charged particles, they were essentially electrons, in those days called beta decay. Why do these negatively charged beta particles come out of nucleus, and how do these nuclear transmutations happen? It turns out that this is not mediated by the strong interactions that Yukawa was talking about. You can figure that out by studying the phenomena more carefully. But once you do that, you realize this is a new kind of interaction, not quite as strong as the strong interaction. And so because it was not strong, it was called weak, and the name weak interaction stuff. So the world was beginning to get more complicated already in terms of interactions. We had gravitation until the 19th century, electromagnetism, but now with the nuclear, the new study of nuclei coming in, we had to posit two new interactions, strong nuclear interactions and weak nuclear interactions. In addition, people found that the analysis of this kind of beta decay could never be consistently done without this new particle called a neutrino coming. Okay, so this neutrino is a neutral particle, but unless you bring in this neutral particle, then you mess up certain conservation laws. So, as I said, we already had a new particle called pion in strong interactions. Now, new particle called neutrino coming in. So, by the end of the 40s, the Second World War was over and the world was getting more complicated. America was taking over the world. This was another thing that gave rise to a completely new area of physics, which eventually became pioneering physics or particle physics, the area that Professor Vishwal and Swapna Mahapatra and I, we work on these in different aspects of these high energy physics. Professor Mahapatra looks at more formal things in that, and Vishwal and I look at more phenomenal things in this. But this whole thing took birth in these fascinating experiments called outer space. They come presumably from the interior of stars or in galactic interactions. And these very, very highly energetic rays travel through space and come into when they reach the Earth and the atmosphere of the Earth, they interact with the particles in the atmosphere of the Earth, and then they create a whole shower of new particles. And in that shower of new particles, all kinds of new things can get created. In particular, you see here, there can be pions, there can be neutrinos, and before people had actually experimentally discovered a pion, this is what they did. They waited for literally the heavens to shower, they waited for the cosmic rays to come in, create the shower of particles, then go to nice observing station at a height like somewhere in Ooty or Darjeeling, and put your detector there and simply wait, and you don't, and then look for evidence of these new particles. So pion, as I said, and the muon, this new other particle was discovered in such cosmic ray experiments. So starting from the early 30s itself, cosmic ray experiments were a big thing, but embarrassment, because by the end of the 50s, people had discovered something like 100 different particles, just like the pion and the neutrino and so on. So the name of the game was to sit with some detector at a higher altitude, wait for the heavens to shower, look for new particles in that, attach your name to that new particle, and you had made a great discovery. Okay. But theoretically, of course, things were a mess, because this was a very, very humbling moment for physicists. They had become very arrogant at the time of quantum mechanics, thinking that they had managed to understand the 100 elements of chemistry in terms of just three basic particles, that is proton, electron and neutron. And by the end of the 50s now, there were not 3 elementary particles, but now there were again 100 elementary particles, and the situation looked extremely confusing. And that history in the 60s is very fascinating, and if I have to talk to you about it, I will have to get Sridhar to invite me again to give you a whole talk of what happened in the 60s. I'm particularly fond of that history, but I'll skip that history and I'll tell you where we are at right now. And this is a beautiful picture because it kind of summarizes the whole thing in one slide. Okay. So, as I said here, you have matter, a block of matter, and you look at it at greater magnification, and you see that it's made up of atoms. Here these atoms are neatly arranged on a lattice. At higher magnification, you start seeing the structure of the atom. You see the nucleus, which is in purple there, and electrons which are floating around it. At even higher magnification, you start seeing the structure of the nucleus, which is made up of protons and neutrons. And even more magnification, you start seeing the structure of the protons and neutrons. So the big realization in the 60s was that we are seeing these 100 odd particles because of the fact that those 100 odd particles, along with particles like the proton and neutron, are not elementary particles, but they are in turn made up of some more elementary objects which are called quarks. Quarks are a quirky name, but they were the ones that were given to them by Gell-Mann, who first proposed these quarks. So, what does the world look like now? Which is what we call the standard. I mean, it's got a very, very ordinary name, this fabulous view of the world, which tells you everything about everything. It's got a very simple name, which is called the standard model of particle physics. Okay? And the standard model of particle physics tells you that the world is made up of 6 kinds of particles called leptons, which are particles like the electron. So the electron, as I said, has a negative charge, and there are 2 more particles like that, which is called muon and tau. And these sizes of these blobs here are to indicate the masses of these particles. So they are not all of the same mass. This is lighter and this is heavier. And as I said, there was a neutrino that was discovered in beta decay along with the electron. So every such particle comes with its own partner, the neutrino. So there's the electron, neutrino, muon, neutrino, tau and tau neutrino. These are the 6 particles which are collectively called leptons. And these are particles which may have electromagnetic interaction if they have charge. They have all partake in weak interactions, but they do not have strong interactions. Particles which also have strong interactions are called quarks, and there are 6 of them. And they also have quirky names like up, down, charm, strange, top, bottom. Again, the size of the blobs indicate the mass of these particles. So the top quark is a very heavy object. A very important statement is that uh, the theory that I'm going to describe a little bit, which is called quantum field theory, dictates that if you have 6 of these particles, 6 of the electrons, you should have 6 quarks. There is no way you can have 6 electrons and 5 quarks. They have to be equal numbers of them. And if you don't have that, you run into a mathematical inconsistency. So, just tell you, the top quark was discovered exactly 20 years ago. Exactly 30 years ago. And 30 years ago to the date, almost, in fact, 1 week ago was the 30th anniversary of the top quark. And it was discovered much later than the other quarks. But even before it was discovered, the theorists knew that there has to be a top quark, because if you don't have the 6th quark, the structure would be, the structure of the theory would be completely vitiated. And so these are this is what is called, constitute the matter content of the world. Okay? So all matter is made up of these 6 plus 6 particles. And how does matter interact? There are, of course, different interactions. And in this theory that I am going to now tell you about, these interactions are described again by particles. So the electromagnetism, which is an interaction, is described by particles which are called photons. The strong interactions are carried by gluons, and the weak interactions are mediated by 3 kinds of particles which are called W plus, W minus, Z. Pushing this, we think that gravity should also be mediated by similar particles called gravitons, except we don't have any evidence for that as yet. So a little more about these interactions. As I said, the strong interactions are strong, that's why they're called strong interactions. And if you think they are in some units, that not some units, but on some scale, if you think that strong interactions are a scale or strength of something between 1 and 10, then compared to them, electromagnetic interactions are 100 times weaker, so they are about 10 to the minus 2. Weak interactions are even weaker, so another 1,000 times smaller, so 10 to the minus 5. And you see gravitational interactions at this scale, at this energy scale, are at something like 10 raised to minus 39. So basically, they don't even figure. So in other words, if you take 2 protons and bring them together in a high energy experiment, as they do in these wonderful experiments that we do in CERN in Geneva, let's say you bring 2 protons together at very high energies. These 2 protons will have all these different interactions. They will have strong interactions, that is the quarks that make up the protons will interact through strong interactions. They will also have electromagnetic interaction because both protons are electrically charged particles. There will also be a weak interaction, but the weak interaction will be so small compared to the strong interaction because it's a factor of 10 raised to minus 5 down, so that if you actually look at the picture, what emerges out of this, it will all be dominated by the strong interactions of the protons. There will be a correction coming due to the electromagnetic interaction, and weak interaction will be really difficult to study. It will show up, you'll have to do a very, very specialized kind of analysis of the experimental data to pick out the weak interactions. But gravitation, 2 protons, each proton has a mass, so they both have to interact with each other gravitationally. So the gravitational interaction will be so weak that it's not even going to figure. So there is no way you are going to be able to identify the gravitational interactions of protons through such experiments. In other words, if you were to do these experiments, you can completely forget gravitation. And that's exactly what people have been doing, and that's what we will also do. What is the framework that is needed to study this? As I told you, the 2 major theoretical movements in the 20th century were quantum mechanics and special relativity. So quantum field theory is a kind of synthesis of the ideas of quantum mechanics and special relativity. Why do you need to do that? Because when you study these high energy particles, you are not only looking at a very microscopic domain, but you're also looking at particles with very high energies. And you're looking at a domain where particles are all flying off at the speed of light or close to the speed of light. And you will therefore need to not just do quantum mechanics, but you also need to bring in special relativity to describe all this. That union is called quantum field theory, and one of the two big things that come out of quantum field theory is the existence of what are called antiparticles, which you may have all heard of. It's making the news all the time. So every known particle, the particle list that I showed you earlier, all of them have antiparticles, so that when you bring an electron and its antiparticle, the positron together, they can completely annihilate each other, and energy of the energy equal to the mass of these two particles is released in them. I should pause here and repeat that, because whatever we've been thinking of for the last 2,500 years in this whole understanding of matter through atoms, one thing was a given, that atoms can never be destroyed. That's what people, the philosophers said 2,500 years ago. When the chemists took to atomism, they also said, Dalton actually said, matter can neither be created nor destroyed. Okay? And that held true till the 1940s. In the 1940s, with the coming of quantum field theory, when you bring in relativity and quantum mechanics together, this famous principle of Dalton goes out of the window. Matter can actually be destroyed or created. Matter can be created out of energy. You can create a pair of a particle and antiparticle. Or when you bring a particle and antiparticle together, you can destroy them and just produce energy. There are also quantum field theory predicts the existence of what are called virtual particles, particles which emerge briefly, and I won't go into that in too much detail as I'll come to it as we go along. But these are particles which don't really have, their existence is rather ephemeral. They come and go like bubbles on a pond. The way we understand the quantum field theory is, I should say, even if this doesn't come across very clearly, is that we understand quantum field theory through symmetries. These are mathematical symmetries, and one way of thinking about it is to say that because we don't know anything much at that level in the microscopic domain, it's all like a black box. If you encounter something where you don't know what the structure is inside and you just have a black box kind of picture of it, what you will do is you'll immediately your reaction will be to turn it around to see what happens. You put it up, you bring it down, you move it sideways, you rotate it. You'll do those kind of things to see what's happening and can you make out anything by doing these kind of things. So physicists who work in quantum field theory do more or less the same thing. They do a set of transformations on these very, very subtle systems to figure out what remains constant in these transformations, and those constants are what are identified as symmetries. And there are different symmetries that come into play. There is Lorentz symmetry, which gives you the principles of special relativity. There are other symmetries, but one important symmetry I will mention is something which is called gauge symmetry. And this is a very important symmetry in the context of quantum field theories. Talk a little more about it now. I'll talk about it in the context of what is called quantum electrodynamics. As I said earlier, electricity and magnetism was combined by James Clerk Maxwell to produce what was called electromagnetism or electromagnetic theory. But people realize that we need to actually go to a quantum version of even these field theories. And this quantum version of electromagnetism is called quantum electrodynamics, and is the theory of electromagnetic interactions. So to put it differently, if you are looking at large charge configurations, which are macroscopic, and you are looking at those effects at a macroscopic level, then you can work with Maxwell's equation. But if you want to study about this at a microscopic level, actually look at the interaction of an electron with a positron or a proton and so on, then you need to go to the quantum version of it, and that's quantum electrodynamics. And as I told you earlier, the electromagnetic interactions are mediated by photons. And I also told you that the magic factor there was something like 1 over 100. The 1 over 100 is the coupling of the photons with particles like the electrons. So coming here, this wiggly line is what is a photon, and these straight lines are the electron with positrons. It's just a diagrammatic representation of what could happen if you bring a electron and a positron together. And this is the coupling of the photon to these charged particles, and that has a strength of 1 over 100. So there's a factor of 1 over 100 sitting at this vertex, there's a factor of 1 over 100 sitting at this vertex. So the thing is, this is only one of the things that can happen when you bring an electron positron together. In fact, what can happen is also this. The way this is different from the earlier diagram is that you now have an extra photon that's being short of this electron, and so this is also going to give a contribution to whatever you are going to measure. And what you have to do is systematically develop a way of keeping track of all these possible diagrams that can contribute to the electron positron interaction. And it turns out that actually this works very well when you do it this way. I apologize for this old figure. It's not a very recent figure, but it kind of tells you that these data points, which are experiments, where this experiment is actually being done. You take a electron beam and positron beam and actually study this. And these data points are the measurements made from such experiments. And those are all these main points that you see here. And this curve is actually the theory that is predicting it, and turns out it's pretty much in agreement with that. The problem, however, is that there can be a lot more that can happen in these diagrams. For example, I looked at I was saying that one kind of diagram is where you can just let a photon get away from an electron like this, but you can also have more complicated diagrams where the photon is emitted and it loops back and connects back to the electron. And these kind of diagrams, these loop diagrams are notorious. And that is because in these loop diagrams, energy conservation or momentum conservation is not guaranteed anymore. So actually, to put it in one word, when you actually calculate these diagrams, it turns out that you get infinities. You get the answer to all these calculations turns out to be infinite, which is absurd. Why is it absurd? Let me go back to this. I said, in this place I had a factor of 1 over 100, here I had a factor of 1 over 100. And when I'm doing this kind of systematic calculation, then I say, oh, but what about a diagram where I bring in extra photon? But then I have to pay a factor of 1 over 100 for that extra photon. So this diagram, compared to the earlier one, is down by a factor of 1 over 100, or 1 over 100 square in fact. But these diagrams, I would have expected to be even smaller because they have two couplings here, so it should be 1 over 100 and 1 over 100 here. It will be even smaller contribution. But when you actually calculate it, it gives you a mathematically absurd answer which is infinite. And this whole thing led to a whole lot of confusion for some time till it was solved by three very, very wise men, Feynman, Schwinger and Kamnaga, actually understood the way to get around these problems, and that they got the Nobel Prize for this work. And they showed that actually that this theory that we are talking of, quantum electrodynamics, this theory has a symmetry called gate symmetry. And this gate symmetry is what rescues the theory from these infinities. And they actually showed that these things are all tied up together, that there is a symmetry in the theory, that this symmetry is a mathematical symmetry, and that leads to an infinite range of interaction. What does that mean? That means that if I have an electron here and an electron somewhere in Mars, they'll still have some finite interaction. Okay. Only at infinity does the interaction between two electrons become zero. Okay. So the range of interaction between two electrons is infinite. So that comes out of the fact that the symmetry, that there is a symmetry in the mathematical symmetry in the theory. That tells you that the carrier of the interaction, the photon, is massless. And if all these three are taken into account, it tells you that the theory is renormalizing, which means that you can get rid of all the infinities that these diagrams give you. These infinities that came here can actually be gotten rid of by proper redefinition of things, and so they showed that you can get rid of those infinities, and that is tied up with to all these three facts: the fact of gate symmetry, the fact of the infinite range of interaction, and the fact of photon being massless. And this theory, after these three people showed as renormalizable, it was applied to various phenomena, and it's really the best tested theory we have. And therefore it becomes a prototype for all other interactions, for studying all other interactions using quantum field theories. And to tell you how good the theory is, I'll take one example, which is the electron. You don't have to know what this is, but this is something that has been calculated in theory. It's called the electron anomalous magnetic moment. It has been calculated in theory very precisely and measured in experiment very precisely. And this is the level of agreement between the theory and experiment. You can see up to what decimal space, and this is all multiplied by 10 to the minus 12. So what decimal place these two agree so beautifully. In fact, this is the best agreement between theory and experiment in the history of science. There is nothing in any science which is as good as this. So obviously when you have a theory for electromagnetism as good as that, you want to then understand whether the nuclear interactions can be understood in quite the same way. Turns out to be not so easy. One, because the strong interactions are very strong. So the particles involved there are quarks, which are the analog of the electrons. The analog of the photons are gluons. But the problem is that the strong interactions are strong. If you remember that in this case you have got a factor of 1 over 100 for every photon that you emitted. In the strong interactions it's a factor of 1. So you're not really being able to gain anything by emitting a gluon. It's the same strength. And this leads to technical problems which maybe for the want of time, I don't know. No, I think I'm really overshooting myself, so I'll cut this short. Maybe I can take some questions. But okay, it leads to certain technical problems. So actually, okay, let me summarize this in one sentence. As I said, the strength of the interactions, of strong interactions, is something like 1. Okay? But that 1 turns out to be something that is at low energies. Turns out that when you go to high energies, the strength of strong interaction, which is actually quite surprising, runs down, and it runs down to becoming something
like 1 over 10, 0.1. So at high energies, which is where we are doing our experiments, strong interactions are still strong, but not quite as strong. And then, because they are not quite as strong, it becomes tractable. It becomes possible to use the theory which is very much like quantum electrodynamics. And I won't go into these details, but again, I just want to show you this agreement between theory and experiment. So you do like this calculation you did with electrons and positrons, now you do it with quarks and gluons. And you see now here these circles, the black and white circles and triangles are data points, and these histogramic curves are theoretical predictions. And you can see that this has taken time. This has taken like 30 years of hard work, but over those 30 years, you have this kind of very, very good agreement of theory and experiment. So it's something we can really, really be proud of in particle physics. What about the weak interactions? Weak interactions are weak, so you should not have the problem of strong interactions, right? So you should have thought it's easier. But the thing is, weak interactions, just like strong interactions also, but weak interactions are visible only at the length scale of the nucleus. They are short range. I mean, the range of interaction is of nuclear size. You don't see weak interactions at macroscopic scales. Whereas, as I said, electromagnetism was infinite in range. So you needed that infinite range for it to have a gauge symmetry. So if weak interactions are short range, how is it then possible to describe it in the same way as electromagnetic interactions, which are not short range but rather infinite range? So can you describe it in terms of a gauge theory like electromagnetism? The initial answer was no, but eventually the answer became yes, and that is because of some realization that gauge symmetry can be what I put this in quotations. It's a catchphrase, spontaneously broken, and in order to do this spontaneous breaking, you need to bring in a new particle called the Higgs particle. Higgs is actually the name of a person, a physicist, Peter Higgs, who first described this phenomenon. And this Higgs particle actually does the full job for you. It allows you to have a gauge symmetry, but it also allows you to have short range of interactions. It allows you to give masses to those W and Z particles. Again, I want to leave you with an understanding of how well theory and experiments agree here. And